Okay, let's talk about, I wanted to do a couple more examples of what we were talking about at the end last time, which was converting NFA to DFA. And this is referred to, like this specific procedure that we're talking about here is referred to as the subset construction. It is a fact that every NFA can be converted into a DFA. And so from a theoretical point of view, these two types of machines have the same capabilities. Even though NFA, there are things that are allowed in an NFA which are not allowed in a DFA. It turns out those extra sort of allegedly more advanced capabilities actually do not lead to any actual difference in the kinds of things that it can do. Anyway, this is called the subset construction, and it's kind of like what you were doing on the quiz. That thing on the quiz is called the product construction. But let's just do another example, and then I'll have one for you to try. There's not really all that much to be said about it. You just have to kind of see how it works. So here is an example. This one, if I were to, so this is my NFA, and then our goal is to convert that into an equivalent DFA. This is an NFA which, if I were to describe in words, something like this accepts any strings where the second to last letter is a, right? This means you can do anything at the beginning, then a, then one more letter, and it will be accepted. So I would say this accepts strings where the second to last letter is a. And anyway, the way that we work this out, now this is kind of an easy one because there are no epsilons. The epsilon transitions make this, I wouldn't say hard, but it's easy to mess it up if you're not super careful. But anyway, this one should be fairly straightforward. We begin with just the set of S as my starting state. Remember, the starting state consists of the original starting state together with any other state which is reachable by epsilon from the starting state. And in this case, there are no epsilons, so we don't have to worry about that reachable by epsilons business. All right? And now let's draw arrows. So I'm going to draw a arrow. This is my DFA, by the way. I'm going to draw a arrow from S to all possible, to the set of all states that are reachable from S by a. And if you are at the state S, where can you go? If you see an A, well, you could go back to S or you could go over to T. So I'm going to say S comma T with an A like that. That's because starting in state S, if you do A, you can either stay in state S or you can go to state T. All right? What about the B arrow? Can anybody say? From S, what's the set of states reachable by a B? What do you say? Yeah. Just S again. Yeah, great. Just S again with a B. All right? And we sort of continue in that way. So you have to, just like the one you did on the quiz, you have to sort of invent new states as needed. But we're just going to draw arrows. How about, can we just, I don't mean to call you out, but can we just like go around the room? Each person can tell me one of the arrows. So how about Tom? From S and T, the A arrow, what do you say?
Would be T and U.
T and U, yes. And also S perhaps?
Oh, yeah.
Yes, so you actually have to, we were all waiting patiently for Tom. You have to look fairly carefully at the diagram to make sure you get this right. But the question is, if I start in either one of these states and do an A, where could I end up? So you can end up in U by doing A from T. You can end up in T by doing A from S. And you can also end up in S by doing A from S. So the answer is S, T, and U. Stew. All right, thank you, Tom. What do you say for the next one? I mean, the next one, by which I mean this one, if I do a B. Sorry, that was unclear.
Maybe S and
I think it's S and U. Yeah, if I'm in state S or T and I do a B, where could I end up? I could end up in U from T, or I could end up in S from S. You cannot end up in T, though. So S and U, I guess I'll go down from there. S and U. And just because I did this before, I happen to know those are all the states we're going to need in this diagram. Okay, so those are all the arrows from S and T. How about the S, T, and U? What do you say? What about the A arrow from S, T, and U?
Does it just go backwards? Or back to S and T?
I think it goes back to itself. Yeah, S, T, and U. If I do an A, I could go from here and get to S. I could go like that and get to T, or I could go like that and get to U. So S, T, U with an A goes back to itself. What about with the B? What do you think?
S or U?
Yeah, I think only S or U, because you cannot reach T by doing a B from any of those states. All right. And we need arrows from S and U. How about the A arrow? What do you think?
It can go to S and T.
S or T. Yeah, I agree, but not U, because you have to start in T to get to U, and you can't do that. So S and T, that would go straight up on my picture with an A. And then from S and U, maybe I'll do this one to bring it home. From S and U with a B, I could end up in S again. I think that's it, though. You cannot end up in U doing a B by doing S and by starting from S or U. So the B arrow is like that from S and U. Okay, and I think that's it. Those are all the arrows, all the states. I hope we remember I said last time the accepting state here is just any of these states, which includes any of the accepting states here, becomes accepting. So down there, anything with a U in it is accepting. And there are two of them. There's this one that has a U in it, that has a U in it. All right? This is how we do the subset construction. Like I said, this is kind of an easy one because there were no epsilons. Every time you look at these, you have to ask yourself, for example, like this arrow, well, how about like this arrow A means if I start in state S and do A, perhaps in combination with epsilons, where can I end up? The epsilons were not an issue here, but more generally they will be. Any questions about that? I got one for you all to try, and I think this is, all we need to say about it. It's an important thing that this is possible to do, but when it comes to actually doing it, it's not so difficult. Although this one is, I will say, a little tricky, just because there are some epsilons, which you will see immediately. The epsilons make things quite a bit more touchy. Like it's really quite easy to mess these up, in my opinion, even if you know what you're doing. I have uninteresting names for my states here. All right, Q1, Q2, Q3, Q4, Q5. Maybe I'll just get it started. So first of all, what shall the starting state be in my subset machine? So this is the NFA. I'm going to draw the DFA as always. The starting state consists of the original starting state together with any other state reachable by epsilon from the starting state. In this case, that means Q1 and Q4. So Q1 is the original starting state. Q4 is reachable by epsilon from the starting state. So it's like that. Q1 and Q4 is where we begin. And then let's just say, where does the A arrow go? And then I'll let you guys do the rest, but I just want to get us started here. Where does the A arrow go? So the question is, starting from either state, Q1 or Q4, and you do an A, where could it end up? Yeah?
Just back to itself.
Back to itself is the correct answer. Yeah, Q1 can go back to Q1. How do you get to Q4 from Q1 or Q4 doing an A? Yes, you can do. So starting in Q1, you can do A followed by epsilon and get to Q4. So you have to allow for when I say like this A arrow actually means A combined with epsilons either before or after or perhaps both. Here I did a followed by an epsilon. In a more complicated diagram, you could do something like epsilon, epsilon, A, epsilon, or something like that. And you have to make sure that you consider all of those possibilities. All right, see if you can fill out the rest of the diagram here. Here's a little hint. When I did this, and if you do it correctly, you should only use 3 states. I mean, your DFA down here is only going to end up with 3 states in it. So if you ever find yourself creating more than 3 states, you messed it up. All right, let's chat about these. I know some people are still working out the details, but I hope you agree with me now that this is not, like the idea behind it is not really hard, although when there's epsilons in there, you have to be very careful about getting everything exactly right. Anyway, Q1, Q2, Q4, Q5 is the state for this one. Now, if I do B from here, I think that goes back directly to itself. 1, 2, 4, and 5. So I can get to 1 by just doing B here. I can get to 4 by doing B followed by epsilon. I can get to 5 by doing from here epsilon B, or maybe just from here B. And I can get to Q2 by doing B from there. You cannot reach Q3 by doing a B from anywhere, though. Okay, and then the last state that I drew was Q1, Q4, Q3. I'm not sure why I put them in that order, but I had an A like this, a B like that, and an A like that. I don't know if we need to talk through the whole thing, because I think everybody eventually wound up at something very much like that. Anybody got questions about these? One last thing that I should do is indicate the accepting states, and remember the accepting state is just any of these which contains one of the original accepting states. So those would be Q3 and Q5. So this one has a Q5, so that is accepting, and the one at the bottom has a Q3, so that is accepting. That's it. All right. Any thoughts about that one? This is, I think, all we need to say about the subset construction. Fairly easy idea to do, although the details can be slightly confusing from time to time. You'll have some more practice with those on the homework. All right. I think we got another 13 minutes. That's enough time to start talking about the next big thing. This was NFAs, and this is kind of all we're going to say about NFAs, at least for now. NFAs are interoperable with DFAs. They can be sort of converted back and forth. Every NFA can be made a DFA like this. And every DFA, how do you convert a DFA to NFA? Well, a DFA already is an NFA, so we don't even really talk about converting DFAs into NFAs. All right? I think we can get started talking about a new type of machine. Can you believe it? A new type of machine I want to discuss. This is a new type of machine which actually people generally don't even think of this as machines, but it's called regular expressions. All right? This is another kind of a string accepting machine, although it doesn't really look like a machine at all when you write down a regular expression. So this is a string accepting thing, but it doesn't look like a machine at all. You don't draw it using states and arrows or anything like that, really. It is, though, a way of accepting or rejecting a string. It looks like this. Here's an example of a regular expression. AB star A plus B star A B A. Something like that. That's a regular expression. This is a somewhat complicated regular expression. Regular expressions are actually used all the time in real life programming. Unlike NFAs and DFAs, they are kind of abstract theoretical things. But regular expressions, actually people use them all the time. If you've done some somewhat fancy programming in the past, you are already familiar with regular expressions, perhaps. But anyway, that is an example of a regular expression, and it defines, if I call that, say, R is this regular expression, it defines a language just like a NFA or DFA would, which we write as this, L of R. And you have to just know how to read this. Because I know how to read regular expressions, like in this case, for this one, I happen to know that, for instance, ABA is in the language generated by this regular expression. Also, AA is, but AB is not in the language generated by this expression. You just have to know how to read that jumble of A's and B's and parentheses and stars and so on. All right? And just, this is like a cultural thing, I guess. These are, like I said, used all the time. And the way that people talk about regular expressions when they're using them in real life, we say, the kind of terminology that people use, we say that R matches ABA. In the terminology that we've used in the past, I would use the word like accepts, like a machine accepts or does not accept a string. But when we're talking about regular expressions, generally people use the word match. So we say that R matches the string ABA. This means accept. But we don't say accepts when you're talking about regular expressions. So don't say that about regular expressions, but that's what it means. All right? So what you need to understand is just how do you look at one of these things and figure out what it's supposed to be, what all of that means, right? And similarly, like if you wanted to make a regular expression to do something or other, how do you build that out of these things? What you see in there, so a regular expression, and actually in real life, these are written. People write that for regular expression. I'm not sure how people pronounce this word. I have used regular expressions a lot in my real life and in programming things that I've wanted to do, although I don't usually talk about them with other people. I think people say regex. Does anybody know? Any of you talk about regular expressions all the time in the club or whatever? Don't say it wrong in the club. I don't know how to say it right, though. I have mixed results in the club, as you can imagine. Anyway, a regular expression here, it consists, like you can tell from that example that I wrote, it consists of alphabet letters, like the A and the B, and those represent, they represent the A and the B, just like we're used to. Alphabet letters, together with operations, and there are 2, maybe 3 operations. The operations are plus and the star. So you saw in that example that I wrote up there. These are 2 different operations, and then also parentheses, if you want to count that as another type of operation. All right, so I don't know if we're going to get all the way there today, but I would like to describe what is the meaning of each of these things. I think we can do this in our remaining time, and then we'll do a bunch of examples next time. So first of all, parentheses are like they are used in math. So parentheses just mean groupings. All right, so in that example that you saw up there, for instance, I have this parentheses, AB in parentheses star, and that just means the star operation applies to AB as like a chunk, all right? It's exactly what you think the parentheses should mean in ordinary mathematics, all right? Let's talk about the plus and the star. So the plus, basically speaking, means or. The star does not mean and. The plus means or, all right? For example, if I say if I just say the regular expression A plus B, this matches A, if I were to write it as a set, the set of A together with B, right? A or B. So the plus, I think, is very easy to understand. So when, I'm just going to scroll back to that somewhat complicated example. This example here, basically what this is going to match is 2 separate types of things. It matches all of these things or these things, followed at the end with a A. That's sort of how you should read these parentheses here with the A afterwards. So this regular expression, it matches kind of 2 different types of stuff. This type with an A at the end, or this type with an A at the end. All right, anyway, that's what the plus means. Generally speaking, if you want to write something sort of like abstract about it, if I have 2 regular expressions and I combine them with a plus, What is the language of that? That is the set of all things that match that is just the set of all things that match the first one, union the set of all things that match the second one. So the plus really corresponds very cleanly with the word or in set theory, the union operation. All right. Okay, what about the star? The star is not so hard to understand, but I suppose a little bit more complicated. This means I'm going to write some somewhat cryptic language here, and then I'll talk about it. This matches the preceding expression 0 or more times. All right? 0 or more times. So it basically represents repetition, although I'm not going to use the word repetition for reasons that you'll see in a moment. But for example, A star, this matches empty string A, etc. Right? 0 or more times. So the empty string is always matched by anything with a star. But then other sort of repetitions, although I don't like that word for reasons you'll see in a moment. All right, as a set, the language of A star is just like A to the n, all right? So the star, you might be tempted to think of the star as just like to the n, although that's not really a good way of thinking about it. You'll see in a few more complicated examples. Okay, what about, here's where it gets a little more interesting, I suppose. A plus B in parentheses star. What this matches is anything that fits these parentheses 0 or more times. All right? So this actually matches something, well, it matches the empty string because it's a star. It could be 0 times. Or something like AAA. That is, if you go through this 3 times and you choose the A every time. All right? But it could also match something like ABA. So the way that the star interacts with the plus is a little bit non-obvious. And this is why I don't really like to describe the star as repetitions, because you're not necessarily repeating the same thing every time. The thing inside the parentheses can be A or B, and you can make different choices each time. So this does match something like ABA. It just means you run through this expression as many times as you want and match whatever that matches as many times as you want. So can anyone describe, like, what, just in words, like what are all the strings that this would match with? Like, for instance, does it have to start with an A? I don't think so. What are the requirements?
It's like all strings in the language of A and B.
Yeah, I think really this just matches any string which is made up of A's and B's, or even the empty string, right? So this actually matches all strings on A and B, right? In other words, actually, the traditional way of writing this, the language of A plus B star, like that, you know, earlier in the course we wrote that like this, AB star. And that's why the star is used in both senses, like this star. The point of this star in regular expressions is it works like this star in set theory does. All repetitions of things from this one or that one. Yeah, and then let me just say one last thing. This is kind of like a sort of hidden operation, I guess. Also, concatenation. This is a fancy word for just writing stuff next to each other. And you can get more interesting things like, for instance, A plus B star B. What that means is something that satisfies that first thing with the star immediately followed by a B. So what I'm talking about here, this matches all strings ending in a B, right? It could be any business from here, but then it has to have a B at the end. you could write this as a set. You could say something like XB, where X is in AB star, something like that. How could I match all strings with, begin with an A and end with two B's? That would look like A plus B star B. This has to begin with two A's, then it has anything you want in the middle, and then it ends with a B. All right? This is the basics of regular expressions. We'll do a bunch more examples next time.